So here's another problem in WANCAT 5.2. So the question is, what is the temperature and vapor mole fraction if the pressure is 1 atmosphere and we have 3 components, isopentane, N-pentane, and N-hexane. So once we have more than 2 components, we now have a multi-component equilibrium problem. And unfortunately, these problems cannot be solved simply using Raoult's law or a simple equilibrium relationship. Generally, what we use in multi-component problems is something called k-values. So the k-value of a component is equal to the ratio of its vapor fraction to its liquid fraction. And there's nothing particularly special about this except that there's lots of correlations that exist to calculate these k-values, and from that we can use this to determine the equilibrium values of a lot of different multi-component mixtures. And usually the equations that we use with these allow us to converge rather quickly, even if we have to do some iteration to get there. So to solve this problem in particular, we're going to use the Priester charts. So I'm just going to make one. This is a Priester chart, and it is a graphical method of finding the k-values of your components. So each squiggly line on this chart will correspond to a specific chemical species. So you need to find a chart that has your chemical species on it. After that's done, you need to know the temperature and the pressure of the system. So obviously, we don't know the temperature of the system, so we're just going to guess one. So we'll start with a guess of 50 degrees Celsius. You first find where 1 atmosphere, since that's our specified pressure, is on this graph. So let's just say it's here. You then find where 50 degrees Celsius is on the t-axis. So let's hypothetically say that it's here. So let's say this is 50 degrees Celsius. So what you do now is that you draw a line that goes straight from your pressure point to your temperature point, like this. Where this line intersects with your squiggly lines corresponds with the k-value of the component specified by that squiggly line. So let's say this, if this was isopentane, then your k-value would be found right at this point here. What we want to do here is we want to find a value of T such that the sum of all the liquid mole fractions multiplied by their k-values is equal to 1. This is when we know that the solution has completely converged. And so if you go through the motions and you find the k-values for the Priester chart at T equals 50 degrees Celsius, you'll find that KIC5, KNC5, NC6. Now that we have the k-values, we can do the summation. So we have 0.15 times 2.02, 0.30 times 1.55, 0.55 times 0.56, and all that is equal to 1.076. So this is not equal to 1, which means that our solution has not converged. So how do we improve our guess for T? Because ultimately we're trying to find the correct T which satisfies this relationship. Now we're going to use a reference value of K in order to improve our temperature guess and help us converge towards the right answer. So the reference value is just going to be the K value of the most abundant component. So in this case it would be N-hexane. So we're going to take KNC6 and use that as our K-ref. So KNC6 equals K-ref. To converge our system, we're going to update our reference K value. So how this is going to work? So we're going to calculate a new value of KNC6 by taking our current value of KNC6, dividing it by the summation. So dividing it by the sum of xi, ki. And what this gives us is in fact 0.56 divided by 1.076, which is equal to 0.52. We go back to our depreciation chart, and we find where the corresponding K value falls on the corresponding component. So let's say this last squiggly line is for N-hexane, and so we find where K is equal to 0.52, and let's say it's right here. We'll retrace our line so that the line goes through P once again, because P does not change, and it goes through this point here and intersects with the T axis at a different location. And wherever this intersects with T is your new temperature. And if you do it correctly, it should give you a value of approximately 47.5 degrees Celsius. So from that, we recalculate the new summation of K. We find that the sum of KXI 1.024, and so we need to readjust, we need to recalculate a new K value for NC6. So taking the new summation and repeating the iteration, we'll find that the new value of KNC6 is going to be equal to 0.5208. 0.5008. So 0.508. Sorry about that. And so after that, we repeat the same exercise on a depreciation chart. So let's say this is where the K value is, and we go, once again, we go right back. And so after that, calculating the new value of xi, ki, you'll find that it's equal to 0.995, which is about as good as we can get with a depreciation chart, so we'll stop iterating there. So in summary, this is how we did it. We found the initial K values using the depreciation chart from an initial temperature guess. We then iterated this temperature guess using our convergence function, and we iterated until we reached the correct temperature of 47.0 degrees Celsius.